This video introduces Algebra 2 students to parent functions. Like the word parent function suggests, that means it is a function with the simplest characteristics of a family. For example, in the table below of the following 5 parent functions, a basic linear function is not y equals mx plus b, but simply x. And then, as we will see later on in this lesson, if you multiply x by something and then add or subtract x by something, then you get the more familiar y equals mx plus b, creating the family of graphs of linear functions. However, the parent function is concerned with the simplest version. Take quadratic as an example. Its rule is simply x squared. There's nothing multiplied, added, or subtracted. And these features are the key ones. An x to the first power, that is what makes something linear. The variable x is not multiplied with other variables. It doesn't appear in a denominator, etc. For quadratic, the key feature is x squared. So you're taking the domain or input and you're squaring it, and it creates this well-defined U-shaped curve. Then the rule, which is the symbolic what do you do to the input to get the output, for cubic is you cube the input, and for square root, you take the 1/2 power of the input. So you see the square root there. Here are the graphs. Constant is a horizontal line because the y value, or the dependent range value f of x, is always equal to some value, but nothing is told about x. So x could be anything along this horizontal line. It has a domain that's a set of reals for that reason. The range is always equal to whatever that constant value is. And it's often of interest to find out the y or x-intercept. For a constant function, it's always equal to that c value. You want to, when transforming functions, keep track of where that point goes. For linear, we start at the origin, and then it's up 1, right 1, because the slope is 1. The domain and range are both the set of reals. Then for quadratic, notice what I have here in blue. To find these 3 points, you first remember that the origin is the vertex, and then you go right 1, up 1, left 1, up 1 to find the other 2 points. Don't confuse that with slope, because if you go right 2, it's not up 2. That's because here when I substitute in 2, I get 4, and then when I substitute in 3, I get 9. So it's not linear. So stay close and just track these 3 points. For cubic, it's right 1, up 1, left 1, down 1. And for square root, it's right 1, up 1, and then you have half of a parabola on its side. And if you put in 4, its square root is 2. But the main thing is to have this point, right 1, up 1. So for quadratic and square root, the domain and range are not all the set of reals. Starting with quadratic, because it's only above the x-axis, the range is y greater than or equal to 0. For square root, we have both the domain and range restricted greater than or equal to 0. That factors into these first 2 notes. Anything that does a horizontal transformation, so translations and reflections over the y-axis, because remember it takes a point from the right and moves it to the left, so those are descriptors of horizontal, that will affect the domain. Please be mindful that if you are reflecting over the y-axis, you are negating the x-coordinate. Therefore, the domain should flip because it will be negation of the x-coordinate, and then when you divide by a negative, you change the sign of the inequality. And that makes sense because when you reflect over the y-axis, the graph would be pointing the other way. Similarly, for the vertical translations and reflections over the x-axis, where you're now negating the y-coordinate, this will flip. Or if you're doing a vertical translation, let's say up by 5, then this will go, or say up by 3, then this will start here, and so then the range, you will also add 3 to that 0. 0 plus 3 makes that y greater than or equal to 3. And lastly, the domains and ranges that are the set of reals are never affected by transformations. So for linear, you never have to worry about their domain and range changing from transformations. So in our first 3 examples, we first identify the parent function, which we will often represent as just f of x or p of x, p for parent, and then the final transform function, we will often represent that using g. We'll also state its domain and range. Now, by graphing calculator, I encourage you to use desmos.com, and instead of having that on the video, I will by hand sketch out each transformation one at a time so you could see how the function goes from the parent to the transform version. And then, of course, we want to describe those transformations. So, first of all, in this example, we have the parent graph. P of x is equal to x. So, in other words, we say linear. It's a linear function. Box your answers. The domain and range of a linear function, because I've committed to memory maybe through the help of note cards. I've memorized the table from the previous slide, and so I know that the domain and the range are both the set of reals for a linear function. And now let's talk about the transformations. So here's the parent, the simplest version of this category or family of functions. And the first thing that I want to do is the subtraction, because the order of operations goes like this. You first input a value for x, and then you go through the order of operations. So the first thing to affect it is that negation. So let's handle that transformation first, and then we'll add the 2 at the end. So when you multiply x by something, that is going to be a horizontal stretch or compression or a reflection. Well, let's see here. If it's negation of the x, say I have a point here, negation of the x, makes it go over here, so that's a reflection over the y-axis. Draw that picture every time if you need to remind yourself. But if you negate the x, then it's a reflection over the y-axis. So let me identify that transformation. I'll say reflection in abbreviation, R-E-F-L, subscript y, and then let me draw that. I'll have in blue the parent graph, so that's direct variation through the origin, and now we're going to reflect it over the y-axis. Make that in red. So like this point at 1, 1 will go down to 1, negative 1, and vice versa on the other side. The negative of the x caused that to happen. Now, we want to look at that plus 2. That is on the outside, so to speak, thinking about it like this, like the negative is affecting the x, and then the plus 2 happens after you substitute in x and then let the parent function's characteristics come into play. And it's just linear. So then the plus 2 is a vertical translation by 2. And we're familiar with that because, so I'm moving everything up 2. That's like the y-intercept. This is like slope-intercept form. Now, because linear functions are so simple, they're just x, you can consider a reflection over the x and a reflection over the y as the same thing. So I could write the g of x as the opposite of, and then parentheses, x plus 2. So then I'm kind of seeing this as like an outside thing, or a negation of the y coordinate, or which is kind of how I explained it here, but then I wrote reflection over the y. So it's very easy to just take one over the other because they are giving you the same result. Or if I really wanted to, I could factor that out, and instead of a vertical translation by 2, I could say a horizontal translation by 2. And it's going to look the same. Let me think about that for a second. This is a vertical translation up by 2. And I realized my mistake here. So the transform graph was this. And then that gets moved up too. So let me start with the parent graph. Then the reflection happened. And then that was bumped up by 2. I lost track of that. So now I go up 2. And that's now matching the fact that it either looks like it goes up 2, or, as we see there, it looks like it goes right 2. Again, with linear, you just have to be patient because one transformation looks like the other. But don't let that confuse you. We're going to now move on to the next example. Involving a more intricate function, we get to then clearly have kind of an inner and an outer part of the function. So remember, inner is affecting the domain, and we have this inner invert, outer original. As we talked about at length in class, with the horizontal transformations, because you're modifying the domain before you even input it into the key characteristic of the function here, the squaring, which gives it that well-defined U-shaped curve, then it's the inverse of what you would think. So with addition, that means this is really like the parent graph looks like this in parametric form. So really, even though we see a +1 there, if that means h must have been -1, so then when you're subtracting a -1, it goes to that positive. So it's kind of tricky to think about algebraically. Proceeding with the problem, we see that there is a square of a variable, so the parent graph is going to be quadratic, which is simply just x squared. And then the domain, it's always the set of reals no matter what for a quadratic. And then the range starts out at y greater than or equal to 0, and now we're doing a vertical translation up by 5, so that's now y greater than or equal to 5. If you had Desmos, you would be putting these in one at a time like follows. If it's just x plus 1 quantity squared, your graph should look like something of the following. Because when I put in -1, that goes to 0, and 0 squared is 0. And then when I put in 0, 0 plus 1 is 1, that squared is now 1. But remember, the parent graph was 0, 0, -1, 1, and 1, 1. So it's weird, isn't it? When you add 1 to the input before the squaring happens, before the u is created, then that actually moves it to the left, and that's why we have a horizontal translation left by 1. The negative signals the left direction, HT abbreviation for horizontal translation. And then that +5, that means we add 5 to all the results of the squaring. So the parabola is already formed, we already get this shape, and now we're just going to the y coordinates, and we're going to bump it up by 5. So we get 1, 2, 3, 4, 5. a graph that looks like that, and Desmos would give you this step by step, and you would be able to visualize what's happening in the symbolic. So we also have a VT by 5. By inner, I mean this. It's inside the parentheses grouped with X, addition or multiplication. And then by outer, I mean the stuff that's happening either here, like not in this case, or out here. It's the stuff that happens after the parent graph already takes into account what's happening. So in this case, the squaring is the key feature to look out for a quadratic. For the final problem, we have a square root. So the parent graph, just square root, and it looks just like this. What should come to mind are what the domain and range are, and kind of what the graph looks like. 1, 1, origin, right 1, up 1, and then just kind of like fan it out as half of a parabola. You don't have to go out 4 and then up 2 and make sure that works. We got the gist. That's what transformations aim for. It's so that in your head you could quickly picture the graph and pull out the key features. It's not really meant for graphing very detailed functions on a coordinate plane. So we now move to the domain and range. And if you want to do the transformations before that, that's probably not a bad idea. But for this one I will, because it's kind of complicated. There are 3 transformations. Remember, to kind of do order of operations, we need to substitute in x first, so to speak. That's where the problem is born. That's like the navel of the function is always where the x is. The first thing we're doing is adding 3. Now remember, inner invert. So what that means is if I add 3, then I need to go to the left by 3, and then I get a graph that looks something like that. So that is a horizontal translation to the left by 3. And if that's still confusing for you, make a table, because if you have x and g of x, and you substitute -3 and then add 3 to it, you get 0. And the square root of that is 0 times -2 is 0. And so again, you're still on the x-axis, so that y-intercept has moved to the left 3. Now let's go on the outside, handling the negative separate from the 2. Remember, when you multiply by a negative, it's a reflection. And because this is outside, just like this, any addition or subtraction out here would be outside, that is a vertical change. So that negation is basically saying you're going to take all the vertical components, all the y-coordinates of your transform parent graph, and then you're going to negate them. So this then is a reflection over the x-axis. So when you negate the y-coordinates, it reflects over the x-axis. And then finally, when we take the 2 into account, covered it up, then and so now we're down here. I don't know exactly where that's going to cross the y-axis. Don't mistake it for crossing at 2. That's just what it looks like. But I'm keeping in mind that this is generally what it looks like based on transformations. If I want something a little more accurate, I could pull out the technology of a calculator or do more substituting in a table. But we just need the gist here. And then multiplying outside by 2, that is a vertical stretch by 2. Because it's going to double all the y-coordinates. So now the graph would look something like that. And again, explore all that on Desmos. Moving to the next page, here we are given a few data points of a function. After we graph the data, we'll be able to visually see what parent graph we are working with, and then through a clever use of the table, we'll be able to deduce what the transformations were. You can't always deduce transformations from a table or a graph, but in these exercises we will make sure that's possible so that we could practice. So graph the data. Notice it goes up to 12 for the y-coordinate, and it goes as low as -2 for the x and as high as 2. That'll help us create the right perspective for our graph. So I don't want to put really anything in the third and fourth quadrants, is what I'm getting at. It's not super important to have the most detailed graphs because we have the graphing technology to make them exact. Plot the points that you have. Kind of getting a rough gist here. And yeah, that helps me figure it out. That's a parabola. So it says describe the parent function. So the parent is going to be quadratic. And so that looks like y equals x squared. I'll call it, using function notation, parent graph of x is equal to x squared. So that's part of the answer. And the approximate transformation, so let's use the table. Now that we know it's quadratic, we know that a quadratic function with its parent graph, p of x, should have the following 3 points. -1, 1, 0, 0, 1, 1, because we memorized that from the table. And then we have the transformed graph. Let's call this g of x. Well, when we substituted in -1, we got 3. So when we substituted in -1, we got 3. When we substituted in 0, we got 0. And then when we substituted in +1, we got +3. Well, the x-coordinates were the same, so it wasn't a horizontal transformation, but it was the y-coordinates that were modified. So it went from 1 to 3, 0 to 0, 1 to 3. So it's not add by 2 because then 0 should go to 2. But so it's not addition or subtraction, it must be multiplication since 1 is the, when you multiply that by any real number, you just get 0. So to get from 1 to 3, we must have multiplied by 3. So vertical stretch by 3 is going to be the approximate transformation. In this case, it's the exact transformation. In the next problem, make a quick graph realizing the x's go from -3 to 3 and the y's go from -1 to 1, but there's also a -1/27th, so maybe we'll count by 1/9 on the horizontal axis, or we could just guess. So -3 to 3. If I don't put markings, then I'm implying that they are 1. Then we have -3, -1. We have -1, -1/27. It's just below the x-axis. That's good enough. We're at the origin, just above the x-axis at 1, and then 3, 1. That's kind of tricky. But we're going to stick with just the 5 parent graphs for now that we talked about in this lesson. So from here, I could tell that the parent graph is cubic. And then let's use a table. I could see that the x-coordinates aren't changing. The y-coordinates, especially like of 1/27th, that wasn't anything on our parent graphs. So I'll set up my table xy. And with the parent graph, we're used to -1, 0, and 1. So I substitute those in to the x column. The y value that we actually get from this transform function is negative 1/27, 0, and 1/27. So what that means is, I guess I wanted to write the parent graph in that column. Always start off with the parent table. And that is for cubic. And then for the other part of the table, if you think that it's the y's that are changing, then put it to the right of the dependent variable column. If you think it's the x's or it's a horizontal transformation, you put it to the left. Just for comparison's sake, it's easier. So instead we got negative 1/27, 0, and 1/27. So how do we get from here to here, here to here, and here to here? Again, if it was addition or subtraction, 0 would have changed, but that's a clue that it was multiplication. And it got smaller from negative 1 to negative 1/27. So we're looking at a vertical compression by 1/27. Wrapping up the note sheet, we have this closure. So explain how to recognize each parent function. You could come up with your own ways of doing that, but linear is a line, quadratic is a U, cubic is like a snake across the x-axis. The square root, it kind of look like that curl to the right kind of looks like a square root symbol, or just remember that it's the inverse of quadratic, so it's half a parabola on its side, opening up to the right or left instead of top or bottom for a regular y equals. But the second closure example, I need to point out something really important. When we are finished practicing the basics of transformations over the next couple chapters, I will start putting problems like this on assessments. I won't at the beginning of the year because I want us to get our feet solidly planted on the ground. But I want to start opening your eyes to the full realm of how transform functions may be presented. Notice here that we have the negation of x. So negation of x means a reflection over the y-axis. And in this problem, what makes it difficult, we have a horizontal translation. When those two are together, think about that. If I have a point here, and then I reflect it over the y-axis, and then I subtract 4, well, does it go this way? Does it go that way? Or do I first take this point, move it left 4, and then reflect over the y-axis? So these things are challenging. So to make the algebra or the symbolic rule as simple as possible, what you will always want to do is factor out the negative. So then what you see is what you get. And this is what I mean. So now we could see that it's x plus 4. And the rule is inner invert. So if we see plus 4, then really the h value, this is a horizontal translation to the left by 4. And then we could say, yes, then we're negating the x. That's a reflection over the y-axis. So really the order kind of would be this, then this. And then lastly, we hit the outside, and then that's a vertical compression by 1/2. That would be the last thing to really hit the problem. So the parent graph is square root, and then we describe the transformations.